Hello, this video presents the method to define the balancing of a 4-stroke V8 engine open at 90 degrees. This method is based on the Cinmot program. This program, I developed myself. It is able to calculate the forces induced by the movement of connecting rods, pistons and balances in a purely mathematical way, and this without correction or simplification factor for any connecting rod, piston and balancer arrangement. The search for a balancing solution for this V8 engine was made possible thanks to the Cinmot program. In order to publicize this program, you can contact me by email. I can search a balancing solution of your engine, compressor or any other mechanical construction involving one or more crank connecting rod piston assemblies. The first search for a solution, whenever possible, will be free of charge. The Cinmot program is more deeply presented in another video on my channel. Title: How to balance an engine easily. Step 1. In order to find the forces and moments generated by the movements of the 8 pistons and the 8 connecting rods, I model, in Cinmot, only those 16 elements. The crankshaft is not included in this calculation, it is as if it were fully balanced. The list of values representing the engine and necessary for the calculation with the program Cinmot. Below is the window where the values are entered. Values which are necessary for the program to calculate the forces and moments induced by the movement of the pistons and connecting rods and without crankshaft effect. And now let's look at the results provided by Cinmot. Results from Cinmot for the 8 pistons and the 8 rods at 1000 revolutions per minute. The results from Cinmot show that forces naturally balance each other. There is only at the 4th order the presence of a small force in Y, but it can be considered as negligible. On the other hand, the moments X and Y at 1st order, or primary order, are strongly present. As 1st order forces are 0, these two moments are called free moments. It's these two moments that have to be eliminated, by means of counterweights placed on the crankshaft, to get a very well balanced V8 engine. As X moment 1st order precedes Y moment 1st order, it's obvious that the counterweights must rotate in the same direction as the rotation of the engine and of course at the same speed. This means that we can mount, on the right place and with the right size, counterweights on the crankshaft. Let's find the value of these counterweights. There are several balancing solutions using counterweights mounted on the crankshaft. One of the solutions is to place identical counterweights on each crank arm and acting in the opposite direction of the crank pin journal. This balancing therefore includes 8 counterweights. This solution is not very elegant, I grant you, but it demonstrates the potential of Cinmot and is a solution. Other solutions will be studied further in this video. Let me show you the crankshaft. This crankshaft, without counterweight, is fully balanced statically and dynamically. The part which constitutes the basic crankshaft, in this engine, and without mounted counterweights, is assumed to be fully balanced statically and dynamically. In other words, the base crankshaft plays no role in the balancing of this engine, only the counterweights, which will be mounted, will balance this engine. Let's calculate these counterweights. Step 2. Now we must define the values of the counterweights to balance the X and Y moments of the 1st order. All these counterweights are identical. In Cinmot I model the 8 counterweights and thanks to the speed of calculation of the program I can use the method that I call, try and see, to find the unbalance of the counterweights. You can follow, on the left, the search for the unbalanced value of the 8 counterweights. Here we go. First, I create 8 balances that correspond to the 8 counterweights. The values introduced, to shorten the demonstration, have been previously introduced. The dimensions and angles correspond to the drawings below. The direction of rotation of the balances is positive because they rotate in the same direction as the engine. The axis of rotation is the axis of the crankshaft, therefore Z. The order is 1 because they rotate at the same speed as the engine. The value of the unbalance of each balancer is, for the moment, 0 kg/meter. Now I am looking for the unbalance of the 8 counterweights so as to eliminate the X and Y moments of the first order. This unbalance is identical for the 8 counterweights. To do this, I use the try and see method. The values that interest us are in the red ellipses. The unbalance is in the vertical ellipse and the X and Y moments of the first order in the horizontal ellipse. The goal is to find an unbalanced value which brings the moments X and Y of the first order to a value close to 0 Newton-meter. Here the search for the unbalance of the 8 counterweights is over. The necessary unbalance is 0.279461 kg/meter and the remaining first-order moments X and Y are 0.7039 Newton-meters, which can be considered as 0. The balancing of this V8 is complete and is theoretically well balanced. Below you can see the drawings of one of the counterweights and the crankshaft with the 8 counterweights. The balancing of this V8 engine is complete. The assembly should theoretically rotate with minimal vibration due to the balancing. To be sure of the result, it would be good to place the crankshaft with its 8 counterweights on a balancing machine to refine it. To do this, the value of bob weights must be defined. This is what we will see in the next step. How to define bob weights with the Cinmot program. Let's do it. To define the mass of the bob weights, it isn't necessary to use Cinmot. It has already given us all the information necessary to find this value. Each counterweight mounted on the crankshaft has an unbalance of 0.279461 kg/meter and as the bob weights must be mounted on the crank pin journal. On the exactly opposite side of the counterweights, they must provide the same unbalance as the addition of the 2 corresponding counterweights, namely 0.558942 kg/meter. As the 2 counterweights are placed on either side of the crank, all we have to do is to place the bob weight in the center of the crank pin journal. The effect of the bob weight will be exactly the opposite of the 2 counterweights. This is valid for the 4 cranks. Drawings on the right show how I calculated the mass of the bob weights necessary to compensate the effect of the counterweights. This mass is 7.12 kg. The bob weights must have a center of gravity placed as drawn at the bottom right. Now the crankshaft is ready to be placed on the balancing machine for final and overall balancing. Then I will still check out these values with Cinmot. Let's do it. Now we are going to check, with Cinmot, if the bob weights are correct and if the crankshaft with its 8 counterweights and the 4 bob weights is statically and dynamically balanced. On the right we find the final calculation of the V8. First I remove the 8 cylinders to have only the 8 counterweights, in other words the complete crankshaft. Second, I add 4 balances to simulate the 4 bob weights based on the previous bob weight calculation and the drawings below. The Cinmot program shows that the crankshaft with its 8 counterweights and 4 bob weights is statically and dynamically balanced at 100%. We can consider that the mass of 7.12 kilograms of the 4 bob weights is correct. The balancing of this V8 with 8 counterweights is complete. The solution found makes this engine very well balanced. The rest of this video quickly presents a balancing solution with only 2 counterweights instead of 8. This has the advantage of reducing the weight of the counterweights and the inertia of the engine. Let's watch it. I am looking for a balancing solution with only 2 counterweights instead of 8 as it is the case in the previous solution but which achieves the same result. I know that the first order moments to balance are 3,875.7993 Newton-meters for X and Y at 1000 rpm, 104.72 radians per second. The 2 counterweights, to be the most effective, must be farthest from each other. These 2 counterweights must be placed at the ends of the crankshaft, namely 361 mm. Calculation of the unbalance required: 3,875.7993 Newton-meters per 2 per 0.361 meters per 104.72 squared 1 per square second gives 0.4895159 kg/meter. The angles where the first order moments x and y are maximal are 243.4 degrees for x and 333.4 degrees for y. By reflection, the start angle of balancer 1 must be 206.6 degrees and the one of balancer 2 must be 26.6 degrees. Let's introduce this in Cinmot. Cinmot is launched and already contains the values of the pistons and connecting rods. I introduced the values of the 2 counterweights previously calculated to see if these values make it possible to balance this V8. Cinmot shows the balancing with 2 counterweights and using the values calculated previously is also a solution that makes this V8 well balanced. I adjust the angles to refine the result. Of course, this is only a theoretical calculation. It will be necessary to find the place for these counterweights without forgetting that this will load the structure of the crankshaft a little more, but that is another matter. Thanks for watching this video. I hope you enjoyed it. Cinmot can calculate all kinds of engines, even, for example, step compressors with different pistons, connecting rods or strokes. In order to publicize this program, you can contact me by email. I can search a balancing solution of your engine, compressor or any other mechanical construction involving one or more crank, connecting rod and piston assemblies. The first search for a solution, whenever possible, will be free of charge. Cinmot is more deeply presented in another video on my channel. Title: How to balance an engine easily. The video continues with a presentation of the Cinmot program and its environment. If you are interested, I invite you to continue watching this video.